Hi everyone. I wanted to give you a summation of chapter 4, and it's been a big chapter, a lot in it. So I wanted to summarize it all for you by showing you our galaxy, our home, the Milky Way, in cross section. So you've seen our galaxy in spiral arms, and that's looking down on it generally, or looking at an angle. This is at a cross-section angle where there is generally the core right in the middle. And we're looking at this across a spectrum that goes from the highest energy waves at gamma rays to the longest and lower energy waves at radio waves over here. So when we talk about hottest here, hotter, warm, lower energy, and lowest energy, we're talking about the wavelength there. What's kind of strange and what you really have to look into here is how these colors come to be, because they are not standard that that red is hot. So there's a lot that you have to analyze when you look in here, and we're just starting to learn all of this, and we'll get better and better at it. But let's start here. So when we look at gamma cross-section of the Milky Way, in this particular one, the heat is red. And in fact, the heat is closer, the hottest heat is closer to the yellow, and the cool is the blue. So you can see that in cross-section, the hottest parts of the Milky Way are right along a line at cross-section for the highest energy waves. Now, when you get to X-ray, it's a little bit cooler, less energy in X-ray, and the colors are different too. In this case, the violet is going to be the warmest, and the red is going to be the lower energy waves. So you see here that this area to the right is really corresponding to the red heat, the gamma rays in this area. Because remember, this is a spectrum. So this is going to be quite hot. This is cooler around here. There is a moderately warm area in the center. And when you go to the visible light, that visible light is white hot for visible light in the center, and it is a bit cooler around these darker areas. That's for visible light. When you get to IR light, infrared light, and infrared energy, that white hot maintains at the core and then really dissipates evenly as you get through the cross section. These are the cooler areas around here. And when you finally get out to radio waves, that's kind of interesting because these are much longer wavelengths that are white hot in here and cooler on the outside. This might be an area that we look into later on for expansion, an expansion of our galaxy from these areas that are at the edges away from the cross section. So I hope that that's pretty interesting for you. We have a lot to go into, but I wanted to introduce the idea of spectra to you. In terms of summarizing this chapter, and it should say summary of chapter 4 up there, not of chapter 3, I'll change that. Again, refracting telescopes have lenses, but refracting telescopes are not in our research our research grouping now. You'll find refracting telescopes that are available for beginners, and they're fine scopes, just not for research scopes. Reflecting telescopes are what we use. That has a primary mirror. Large telescopes have 3 powers. The first one is to gather light from very faint sources, hopefully. The second one is to have very low angular resolution for small angles at long distances. The third is to magnify and have magnifying power. About that resolution, to go back to that for a second, there are limits to that angular resolution, and some of those limits are based on the optical qualities of the mirror or of the lens. Others are based on atmospheric effects. right? So we can use active and adaptive optics. Remember, adjusting the mirrors at Keck to work on that. And remember the lasers at Keck too. Really cool stuff. In terms of some of the other things in regard to resolution and diffraction, interferometry can really improve that resolution and that diffraction, and it's particularly used for radio telescopes, although it is used for optic telescopes as well. In collecting data from scopes that are on the ground or in the atmosphere or in the universe, we use array detectors, or what are called coupling devices. And that data that comes in digitalized is used for intensity measurements, for images obviously, and for spectroscopy as well. Those detectors are used in space for gamma rays, which would eat through mirrors, and they're also used with X-rays as well. The X-ray mirrors are quite different from the visible light mirrors, and that IR and that UV spectra needs to be measured above our atmosphere. So I would recommend that you take a look at some of these terms so that you make sure that you understand them. And if you don't, go back and look over them, because we will be building on this for the rest of the semester. So here's some more of them and what they're associated with. For instance, resolving power is associated with diffraction fringe, remember, around the door, interferometers, and seeing, which talks to atmospheric irregularities, and adaptive optics, which talks to the lasers and the mirrors that you are able to adapt to. So please go over this, because you'll be using them later and you'll feel more confident when we get into more complex subjects. See you on the other side.